Hi everyone, welcome to trimester 2. We are having a fresh start this trimester, so I hope your headphones are in, I hope you're in a quiet place, I hope you're ready to really take some good notes and mark places in your notes where you have questions. Because we're going to start talking about functions, and functions are a little bit confusing and I think new to a lot of you. Okay, so wherever you have a question in your notes, please mark it down and ask me, Ms. Samaru, Ms. Vasquez, Ms. Silverstein for any questions you have. Alright, let's get started. Your aim is that I can define a function and determine if a relationship is a function by analyzing its inputs and its outputs. We're going to use those two words a lot when we talk about functions. So the definition of a function is that it's a rule. I'm going to circle that. It's a rule that converts an input into exactly one output. So you put something in, like basically, you plug in, and you get exactly one thing out. So what do you plug in as your input, and what number do you get when you plug it in? These rules often come in the form of 4 different things. You can have an equation, you can have a graph, a table, and a verbal description, and they all represent the same function. Okay? So let's take a look at an example of a function now that we have the formal definition. So exercise 1, so consider this function rule. So like I said, there's always a rule. Okay, and it usually has to do with how we look at numbers. Are we multiplying, adding, subtracting? What are we doing to the number? So here's the first function we have in exercise 1. Multiply the input by 2 and then subtract 1 to get the output. So we're going to follow these instructions. Multiply the input by 2 and subtract 1 to get the output. So usually your inputs here are always going to be your x's. Okay, x is usually always the input, and your output is usually always a y. Because like we talked about with graphing, you always graph an xy coordinate. So we're plugging in x and we're getting out a y. So the rule says multiply the input by 2. So my input here is 0. So what am I going to multiply the input by? I'm going to multiply the input by 2. So I have 0 times 2. When I multiply 0 by 2, I get 0. And then what's the next step say to do? The next step says to then subtract 1. So then I'm going to take 0 minus 1, and I'm going to get negative 1 as my output. So I plugged in the 0, I did 2 times 0, and then I did that minus 1, and I got negative 1. So now we're going to try it again for the rest of the table. I'm going to do now multiply the input by 2, so my input for this one is 1. Multiply it by 2. 2 times 1 gives me 2. The next step is then to subtract 1. So I'm going to subtract 1, and 2 minus 1 gives me 1. So my next output is 1. In fact, let me be clear here what my input is. So my inputs are these right there. So my next input is 2. Multiply 2 times 2. That gives me 4. And then I subtract 1. So multiply by 2, subtract 1. Multiply by 2, subtract 1. That's my rule for this function. Number 3 times 2 would give me 6. And then 6 minus 1 gives me a 5. Okay? So I filled in my table. That was part A. Part B said, now write an equation that gives this rule in a symbolic form. So this is like Unit 3 where we're translating English to algebra. So I need a variable. And what's the variable in this problem? X. X is my variable. So I know when I write my equation, look at how the green number is changing every time. So that's where I'm going to have to put my X. So I'm going to have X. And what am I multiplying by it every time? Every time the first step I do, I multiply by 2. So I'm going to have 2x. And then what's the next thing I do? I subtract 1. So there's my rule. 2x minus 1, and what's it going to equal? What is my output? Y. So there's my rule. 2x minus 1 equals y. Okay? Usually you'll see it in this form, y equals 2x minus 1. You'll see the y in front. Okay? So that's my equation. Write an equation in symbolic form. Then part C has us graphing it. So I have my graph here, and we talked about graphing the other day. So now I'm going to take this and I'm going to plot my points. So the first thing I need to do is I need to take these inputs and outputs and make them coordinates. So this first coordinate, my x is 0, my y is negative 1. For this one, my x is 1, and y is 1. My x here is 2, y is 3, and here my x is 3 and my y is 5. Okay? Notice that on your grid, your y is your output, your x is your input. Okay? And now we just graph these 4 coordinates. So I'm going to graph, point at 0, negative 1 is right there. The next point is over 1, up 1, right here. I have a point at 2, 3, and a point at 3, 5. And I've graphed my function. Now this function would continue to go, so I'm going to put an arrow at the top. You don't have to put the arrow at the top. Let's actually leave it off because in this table we only have these 4 points. So I'm going to leave it like this. Normally you'd put the arrow if we had, we were talking more about this could go on forever and ever, which it could, but I think for right now we'll just graph this table at this start and this end. Okay? So that's a first introduction into getting a table, making an equation, and then graphing the graph that it comes from. Okay? Exercise 2. In the function rule from number 1, what input would be needed to produce an output of 17? So let's rewrite our function rule from number 1. So from number 1, we had this function rule. We had y equals 2x minus 1. So there's our rule. And this question is saying what input, so in other words, what x value? So input is another way of saying x. So what x would we need to produce an output of 17? So the output is y. So what do we know that y is going to equal? 17. So to figure this out, what do I need to change y into? I need to replace y with 17 and then solve this equation for x. Okay. This is a little bit tricky because now I have to do some solving equations. I can't just plug it in and calculate. So I've got to add 1 to both sides. The 1's cancel out. 17 plus 1 is 18. Bring down my 2x. Divide both sides by 2. And I get that x equals 9. So my input is 9 if I want an output of 17. Okay? The next part of the question says, why is it harder to find an input when you have an output than finding an output when you have input? What that's asking you is that, why is this first part so much easier? When we were just plugging in 0, 1, 2, 3, and then finding the output, this table didn't take us much time. We just plugged it in and calculated. But this took a little bit more thinking. It's harder because we have to solve. We have to do some solving and remember those lessons from Unit 2. So when I answer this question, I'm going to say, it's harder because we are solving, not just calculating. Okay? We can still do it. If I know an output, I can find an input, but it takes a little bit more time. Okay? Exercise 3. A function rule takes the input n and converts it into an output y. So we have our input n and our output y by increasing 1/2 of the input by 10. Determine the output for this rule when the input is 50, and then write an equation. So let's do this first part. Determine an output for this rule when the input is 50. So if I know my input is 50, that means that n has to equal 50. And let's take a look at my rule. My rule says I increase 1/2 of the input by 10. So increase 1/2 of the input by 10. Well, first of all, I have to get half of the input. So I have 50, and I have to get half of it. So I'm going to multiply it by half. 50 times a half, well, what's half of 50? 25. Then the next part says to do what? So that was my 1/2 of the input. And then what do I have to do? I have to increase it by 10. So I have to increase this by 10. So I'm going to have 25 plus 10 to give me 35. So when n equals 50, that means that y equals 35. Here's my input. Oh, the pen did a weird thing. Here's my input, and this is my output. Okay? I put in 50, and I got 35. Now, what's the second part of this question say? The second part of the question says, all right, now write an equation for this rule. The rule of multiply by half and then add 10. So let's take my input n. I multiply it by a half, so 1/2 n, and then I add 10. And what should I get? I should get y. So there's my input, and there's my output. Okay, a function is all about putting in one thing, one number, and getting out a number. Okay, input, output. Exercise 4. Function rules do not always have to be numerical. Okay, and this is where it gets kind of weird. So they simply have to return a single output for a given input. The table below gives a rule that takes an input as a neighborhood child and gives an output the month he or she was born in. So this is a fancy way of saying, you know, you have a kid and they each have a month they're born in. Input the kid, you output a month. So question A says, why can we consider this rule a function? Okay, well, remember the rule of a function. Let's go back to our definition. The rule of a function says that it converts an input into exactly one output, exactly one. You can't put something in and get out two things. So if I look at this table here, is each child have exactly one birth month? Max has one in January. Evan has April. Zeke has May. Rosie has February. Nico has May. Does each one kid have 1 month? Yes. So we can consider this a function because each input, meaning each child, has exactly one output, the month. That's why this is a function. So now let's take a look at B. What is the output when the input is Rosie? So that's basically asking, if we have Rosie, what is her birth month? February. So February. Okay. Letter C, find all inputs that give an output of May. So these are my inputs. Just always label it. These are my outputs, and this question is asking for gives an output of May. So I have an output of May here, and I have an output of May here. So the two inputs are Zeke and, actually this is in a different color here, and that might make it a little more clear. May, and my inputs are Zeke and Nico. So that's the first part of the question. The second part says, why does this not violate the definition of a function, even though there are two answers? Right? Because remember how I said you could only have exactly one output? Well, this is kind of confusing because, look, I've got May listed twice. So the answer to this is actually pretty simple. The answer is that because Zeke and Nico still only have one output. It's okay, I need you guys to really listen to this part and write it down. It's okay that it is the same value output, meaning they're both May. So here's what wouldn't be okay. I think this will make a lot more sense. It would not be okay if Zeke had an output of May and April. Because here you'd have one input here. So here would be your one input. But how many outputs would he have? You'd have two outputs. This is not okay. It doesn't even make any sense. Can a person be born in the month of May and April? No, this is actually impossible. So this is okay. This is not okay. Two different inputs can have the same output, but one input cannot have two outputs. I can't plug in a number, I can't plug in the number 2 and get out 7 and 8. If I take a look at this numerically, let's go back to example number 1. Let's go back here. Notice that when I plugged in 0, how many outputs did I get? I just got the answer of -1. I can't plug in 0 and get -1 and 7. Right? I can't do that. I can't plug in one number and get out two different ones. That would make something not a function. Okay? So this problem really highlights the difference in a function and a non-function. Okay? So let's take a look at this graphically in a situation. So this is the last problem of this lesson, and this is something that we're going to talk about a lot in this unit, about graphing an idea, modeling a situation, modeling a story with a graph. Okay? So this question illustrates something about modeling. So functions are useful because they can often be used to model things that are happening in the real world. The next exercise illustrates a function given only in graphical form. We have no equation, we have no table, we have no rule, we just have a graph that's a function. So we can look at this and answer a lot of questions and think a lot about this situation. So let's read the situation first. So exercise 5 says, Charlene heads out to school by foot on a fine spring day. Her distance from school in blocks is given as a function of time in minutes she's been walking. This function is represented by the graph given below. So before we start looking at the questions, let's look at the graph and try and understand what we're looking at here. On the bottom is time. So on our bottom part is time. And remember what I said about input and output. This x-axis right here, this is always your input. This y-axis is always your output. So Charlene is putting in time and she's getting out distance, right? You're walking, you're getting out distance. So when I look down here, I can say, okay, well, this is one minute, 2 minutes. Sometimes this is really helpful to label these each when you see it, because not everything is going to be labeled clearly. So I'm just going to label these nice so I can see it. On the left side, I have distance from school, and that's very important because this point right here, this point right here is saying that where is she? If she's distanced from school, she's probably here at home. She's starting at home away from school. This right here is when she gets to school. Okay, because she's 20 blocks away from school, here she's 0. So I'm just kind of looking at this graph and seeing, okay, she's starting 20 blocks away from school, and she's getting closer and closer and closer. She's getting closer and closer and closer back to school. Okay, so really pay attention to your sides. The bottom is time, and the side is distance. Okay, now let's take a look at the questions. A says, how far does Charlene start off from school? Okay, well, her initial, when she starts, is at 0. So, how far away is she? She's 20 blocks. She's here when she starts. This is her starting point. She's starting at home, and she's 20 blocks away. B, what is her distance from school after she has been walking for 4 minutes? B says, what is her distance from school after she's been walking for 4 minutes? So now you're looking at time, and you're going to where it says 4. So here's where it says 4, right here, and you're going to think, okay, let's look at her distance. I'm going to go up, all the way until here. And how far away is she? Because you're asking for distance. She is, how would I label this? This is going up by 2's. So I'm going to label that. So she's 14 blocks away after 14 minutes. So notice that this is kind of tricky because these are going up by 2's and the bottom's going up by 1's. You have to pay very, very close attention to your grid. Okay? Letter C says, let me for color, after walking for 6 minutes, Charlene stops to look for her subway pass. So I'm going to go to 6 minutes right here and go up. Here is where she stops, and I can tell she stops because look at this line right here. A flat line means that this on the left is not changing. It's staying at what value? It's staying at 10. So she stays at 10 for how long? From here to here. From 6 to 9, she stopped. So from 6 to 9 minutes, she stopped. And how long is that from 6 to 9 minutes? That's 3 minutes. So your answer here is 3 minutes. Okay. Letter D, sorry, I'm just making some space. Letter D, Charlene then walks to a subway station before heading to school on the subway, a local. How many blocks did she walk to the subway? So after she stops, she walks to the subway. Let me get this color. And this is where she's walking to the subway. That segment right there, she's walking to the subway. How many blocks did she walk to the subway? So now it's asking for this distance from here until here. Well, that's between 10 and 12, so 2 blocks. Okay? Really pay close attention to what the question's asking. If this question is saying how long did it take her, then you'd look from 9 to 11. But because this is saying how many blocks, we need to look at the distance for that. And finally, letter E is asking how long did it take? So we're looking at time. How long did it take for her to get to the school once she got on the train? So here she is getting on the train. And now it's asking how long did it take her to get all the way to school. So that's from 11 right here all the way to 15. So from 11 minutes to 15 minutes. So that is 4 minutes. Okay? Now, when you go to your fluency, there are going to be some questions about looking at coordinates. So, determining whether something is a function from giving its coordinates. We talked a little bit briefly about that in the lesson when we did this question back here about the child and the birth month, and I gave you this example of how you can't have 2 inputs for 1 output. So in the fluency, they're going to talk about numbers instead of an idea. So it's really important that when you guys do your fluency, that you are trying it on your own, you are not copying the answer key, because this kind of math requires some thinking. So do not come to me, or Ms. Vasquez or Ms. Samaru, asking us to do your mastery if you really don't feel comfortable with the fluency, okay? It's a fresh start for you guys, trimester 2. Start learning the material so you can really rock those Regents in June, all right? Okay, good luck on your fluency, and I'll see you next time.